Okay, so what I'm going to talk to you today is about risk assessment of AI-based systems. And before I go into this, I've had a sort of work history of dealing and developing risk assessment systems, and I've always been of the opinion that you can take a well-established, well-founded risk assessment tool or technique and develop it for a different use. And so this is based on that assumption. Okay. So, first of all, I'm looking at manufacturing industry or high-hazard industries. And this is an area where AI is becoming prevalent, and particularly in autonomous systems. And because AI is becoming prevalent in these systems, traditional risk assessment techniques fall short of identifying the new and varied hazards and risks that are associated with AI. And because in the UK we have quite stringent regulations within industrial sectors where there's risk of fatality and so on, these regulations are pretty much based on risk assessment. It's one of the cornerstones of our regulation. So if the risk assessment can't handle artificial intelligence very well, then the risk assessment needs to be adapted to do so. So traditional techniques like hazard and operability studies, like failure modes and effects analysis and so on, can be modified, I believe, to assess AR-based systems. And so what you do is you look at things like changing failure modes that you look with and make them AI relevant, changing different deviations and things like that so that they suit the new technology that you're going to work with. So what I've proposed is that if you look at the risk assessment landscape associated with manufacturing industry, you'll see that there are methods to identify hazards, methods to assess the failure modes that are associated with these hazards, methods of looking at root cause analysis, and then methods at looking what can you do about it and how effective are the mitigations for these. And so these four techniques in traditional high hazard industries can fulfill those requirements. Now these are not the only techniques, but these examples that I'm choosing to look at. So in terms of HAZOP, we look at introducing new guide words that are relevant to artificial intelligence. Misinterpretation, overconfidence, drift, words like that. In failure modes analysis, we focus on AI-related failure modes, like adversarial attacks and training data issues. In fault trees, we account for things like algorithmic branches and their failures. And in layer of protection analysis, we look at what are the mitigations that work to protect against these hazards and failure modes, and how can we ensure that a combination of diverse measures can help reduce risk. So first of all, I went through I thought of a small case study with which to apply this. And then I went against all that I go to companies for and asked them, is this a one-person assessment? And went and did this myself. But all I'm looking at is outlining a possible approach. And hopefully lots of people can say why it isn't possible and help to give improvements. So if we look at an autonomous guided vehicle, whose job is to pick up materials, deliver them to a processing machine, then pick up the finished product and take that somewhere else. And you might think, well, not too difficult. What's wrong with the normal guide wires and magnetic strips for doing that? But what about when your workspace has lots of people who seemingly are at random places and locations, lots of other vehicles, guided vehicles, and so on. And when you've got all of these issues and all of this randomness, then the use of standard guide wires and magnetic guides for routing from one part in the workplace to another are suddenly very ineffective. And so you need something that can look at all the information, make relevant routing decisions, and minimise the amount of downtime and maximise the efficiency. So, let's have a quick look at an example excerpt from a HAZOP study, from a hazard and operability study. And I'm only going to go through one. If we take as a node the AGV navigation system, and we're particularly interested in this case at the sensor input, and we're applying the word misinterpretation. The AGV effectively misinterprets reflective floor as being an open space. And this can be caused by environmental glare, it could be caused by problems with the sensor calibration, and there are a lot more reasons why this can be caused, but it can and does happen. What are the consequences? Well, you can have a collision with either an obstacle or a person. Either way, this is an undesired effect that not only could cause injury to workers, but cause loss of productivity and other similar negative aspects for the company. So, as is common in this type of assessment, we always write down, what do we do at the moment? What have we already got? And in this case, there's a possibility that we have human remote override, and somebody can press an emergency stop button, which brings everything to a safe standstill until the problem is dealt with. But that's actually not much of a response at all, because it doesn't add any benefit of having artificial intelligence. So maybe to look at such a system, we can implement things like real-time sensor data validation, and we can enhance the environmental robustness of the training for the AI system. So we take a lot closer look at the environment and what the problems might be, and that we build that into our model so that it doesn't make an erroneous decision. So then we have a look at our adaptation of failure modes, effects, and criticality analysis. And we'll just go through the top example again. So if we look at the AGV vision system, its function is object recognition. A failure mode that we want to look at could be contextual misrepresentation, failure to interpret its environment correctly. And the effect causes, again, lighting, placement of objects. The list is continuous, but we only put a few example ones in. And the effect on the system is that we could, the vision system could give incorrect information to the navigation system, which could result in an incorrect path deviation, which could then lead to collision or other things. Then we use the risk priority number for those familiar with FAMICA. And we think it's got a high severity, it's marked out of 10. A mediocre probability of occurrence. And then the detection, which is worked inversely, so a higher number is bad. Then failure to detect is a problem. And what we do there is we end up with a risk priority number, which is a ranking number, which enables us to look at what are the worst problems, and that can then guide our effort into what we deal with first. Here's an example fault tree, and we can look down the different algorithmic paths, and we can look at the root causes of path planning failures or obstacle detection and so on. And finally, we look at layer protection analysis, and I've put numbers in, but later decided that trying to evaluate AI-related problems or mitigations is perhaps not necessarily a practical thing. But here we can identify independent protection layers, and we can see that if you have a mixture of AI-related, like algorithmic safeguards, human operator mitigations, and redundant technical systems, that the combination of these protection layers can protect against hazards in an AI-based system. So what I've gone through is a demonstration of how we can identify hazards and analyse the failure modes in depth, look for root causes, and then look to see what type of combination of protection layers can best mitigate against these. So really the conclusion from the case study is the root causes seemed mostly originated from the data pipeline and algorithmic issues. That actually, in reality, a lot of the risks are dynamic in nature and evasive, and that you wouldn't necessarily find out until something had happened, and then you'd further analysed it. We found that data quality and context concept drift can continuously reshape the risk profile, so hence the one-off risk assessment is no longer a viable approach in AI-based systems. We found that it's actually quite difficult to determine the independence of AI-related risk reduction techniques because of a lot of interdependencies. So in suggested mitigations, we think that, this is a piece of work I did myself, but that continuous life cycle manage is important to look at things like drift detection, retraining triggers and bias audits, and you need a life cycle approach to implement those on a continuous basis. And we also think that diverse safeguards, including algorithmic, human and physical controls, are needed to reduce the risks of AI-based systems like this. And there's a need to shift from one-time assessments to trigger-based and life cycle-based AI assessment. And by trigger-based, I mean establishing a number of triggers that would cause you to reassess the risk profile of the system that you're looking at. So then quickly, and a very quick initial look has indicated that it might be reasonable to convert these traditional risk assessment methods for use with AI, but without actually trying it in anger, so to speak. That's difficult to confirm. If this approach did work, as the case study suggests it possibly might, then this would support the UK's regulatory approach and hopefully would be a useful way of keeping risks as low as possible from AI-based systems. Initially, though, I'm saying that this is only the initial step forward in just having a look at these techniques and seeing whether they can be converted. And this could be a small part in an AI-based risk assessment framework that would certainly require a lot more work. And I'm going to shut up there and answer any questions.
Thank you very much. Very well from timing.